When you settle into rest and prepare for sleep, there's a small chance that every sight, sound, and sensation you experience is being generated by a vast computer beyond your perception. The room around you, the weight of your body, the thoughts in your mind, could all be intricate patterns of information processed by an intelligence far beyond our understanding. The idea sounds surprising, but it's something many respected scientists and philosophers actually take seriously. And tonight, as you drift toward dreams, we are going to explore this extraordinary idea, together in the most relaxing way possible. The question of what is truly real has haunted humanity for thousands of years. Philosophers in ancient Greece and China wondered whether appearances could be trusted. But our modern technology has given this ancient question a startling new form. The possibility that reality itself is a simulation running on some unimaginably powerful computer. This is called the simulation hypothesis, and it suggests that everything we experience, including ourselves, might be computed rather than fundamentally physical. It sounds like a movie plot, but the logic behind it has convinced some brilliant minds that it deserves serious consideration. Welcome back to the drowsy astronaut. I'm really glad you made it here tonight, and I know it's been a long day for you. That's why I'm here, to help you unwind and drift towards sleep. So for now, let everything slow down and just rest with me as we explore this topic at a calm, comfortable pace. If you find these journeys helpful for relaxation and sleep, consider subscribing so you can return whenever you need. But for now, there's nothing you need to solve, nothing you need to focus on. Just listen and let the ideas settle gently into your awareness. The simulation hypothesis begins with an observation about technology, that computers have grown exponentially more powerful over the past several decades. Video games that once showed crude blocks now render photorealistic worlds, and virtual reality is becoming increasingly immersive with each passing year. If this progress continues for centuries or millennia, future civilizations might create simulations indistinguishable from physical reality. And if such simulations are possible, the question becomes whether we might already be inside one. The idea seems outlandish at first, but consider the logic carefully. If advanced civilizations can create realistic simulations that contain conscious beings, and if they create many such simulations, perhaps billions of them, then simulated beings would vastly outnumber beings in the original base reality. A randomly selected conscious being would almost certainly be simulated, simply because simulated minds would be far more common than original ones. We think of ourselves as real, as living in base reality, but statistically, if simulations are possible and common, we probably are not. This reasoning was formalized by philosopher Nick Bostrom at Oxford University in a famous paper published in 2003 that sparked worldwide discussion. Bostrom did not claim that we definitely live in a simulation, but he showed that certain logical conclusions follow from reasonable assumptions about technology. If civilizations typically develop simulation capability, and if they choose to use it, then most conscious experiences in the universe would be simulated ones. The argument is not about certainty, but about probability and the strange implications of technological progress. The simulation hypothesis connects to ancient philosophical traditions in surprising ways, questions about reality and illusion that humans have pondered for millennia. But it also raises new questions unique to our technological age about consciousness, computation, and the nature of existence itself. Tonight we will explore both the ancient roots and the modern formulation, moving slowly through the ideas that make this hypothesis so fascinating. Whether or not we are simulated, the question itself reveals something deep about the mystery of existence and the limits of human knowledge. Before we dive deeper into the argument and its implications, let us simply sit with the strangeness of the question itself. Imagine that everything you see and touch is information, that the atoms in your body are calculations in some cosmic computer. Imagine that the laws of physics are lines of code, and that the universe runs on principles we might one day understand as programming. This is not necessarily true, and many scientists are skeptical, but the mere possibility opens doors of wonder that we will explore tonight. The simulation hypothesis invites us to look at familiar things with fresh eyes, to notice the mathematical precision of nature that we usually take for granted. Why do physical laws follow equations so perfectly, as if reality were designed according to mathematical blueprints? Why does the universe seem so suspiciously well organized, with constants fine-tuned to allow the existence of stars, planets, and life? These observations take on new meaning when we consider simulation, suggesting that perhaps someone wrote the rules we live by. But we should approach this topic with gentle skepticism as well as wonder, recognizing that fascinating ideas are not the same as proven facts. Many scientists and philosophers remain unconvinced by the simulation argument, pointing to problems with its logic and assumptions that may not hold. We will explore these objections too, fairly and thoughtfully, because honest inquiry requires considering all sides of a question. The goal tonight is not to convince you that we are simulated, but to explore a profound question about the nature of existence. As we journey through this topic in the parts ahead, we will move from ancient philosophy to cutting-edge physics and computer science. We will examine the logic of the simulation argument in detail and consider what evidence might support or undermine the hypothesis. We will ask what it would mean if we were simulated, and whether that would change anything about the value and meaning of life. And throughout, we will maintain the peaceful, contemplative pace that allows these ideas to settle into understanding without stress. The question of whether reality is real is strangely calming when approached peacefully, because it reminds us how little we ultimately know about existence. We pretend to certainty in our daily lives, assuming the world is as it appears. But the deepest truths may lie beyond our current understanding. The simulation hypothesis is one lens among many for examining existence, and looking through it can illuminate aspects of reality we normally overlook. Long before computers existed, philosophers wondered whether reality could be trusted, whether the world we perceive might be fundamentally different from how it appears. These ancient questions form the foundation for our modern simulation hypothesis, showing that humanity has always sensed something mysterious about existence. In ancient Greece, the philosopher Plato told a story that still resonates today, the allegory of the cave, about prisoners who mistake shadows for reality. Imagine people chained in a dark cave since birth, facing a wall where shadows dance, cast by objects passing before a fire behind them. These prisoners would believe the shadows were real things, never suspecting that the true objects lay behind them, hidden from view. If one prisoner escaped and saw the real world outside, he would realize his entire previous existence had been illusion. Plato used this story to illustrate his philosophy of forms, the idea that our physical world is merely a shadow of a higher reality. The things we see and touch are imperfect copies, reflections of perfect ideal forms that exist in a realm beyond our senses. This is remarkably similar to the simulation hypothesis in some ways, suggesting that what we perceive is a lesser version of something more fundamental. The cave allegory teaches that our senses can systematically deceive us, and that truth might require looking beyond immediate appearances. 2,000 years later, the French philosopher René Descartes posed his own challenge, asking how we can know anything with absolute certainty. Descartes imagined that a powerful evil demon might be deceiving him, creating an elaborate illusion that appeared to be reality, but was entirely fake. This demon could manipulate his senses and even his reasoning, making him believe in a world that did not actually exist. Descartes found only one thing he could not doubt: that he himself existed as a thinking thing, because doubting requires a doubter. The famous phrase, "I think, therefore I am," emerged from this meditation. Descartes' one certainty in a world that might be entirely illusion. But notice what this certainty does not include. It does not prove that the physical world exists, only that thinking exists. The evil demon scenario is remarkably similar to the simulation hypothesis. Both suggest that our entire experience might be manufactured by an external intelligence. Descartes could not prove the demon was not real, and we cannot prove that simulators are not running our universe. The dream argument is another ancient puzzle that undermines our confidence in reality, pointing out that dreams can seem completely real while we are having them. When you dream, you experience sights, sounds, emotions, often without any suspicion that you are not awake in the real world. Only upon waking do you realize the experience was generated by your mind, that the people and places in the dream had no external existence. If dreams can fool us so completely, how do we know that waking life is not also a dream of some kind? The Chinese philosopher Zhuangzi expressed this beautifully over 2,000 years ago in his famous butterfly dream that continues to puzzle readers today. Zhuangzi dreamed he was a butterfly, fluttering happily through a garden, completely unaware that he was actually a man dreaming. But when he woke, a strange question occurred to him. Was he a man who had dreamed of being a butterfly, or a butterfly now dreaming of being a man? Neither answer could be proven, and the boundary between dreamer and dreamed became uncertain. Eastern philosophy offers the concept of Maya, particularly in Hindu traditions, the idea that the perceived world is a kind of cosmic illusion. Maya does not mean that the world is fake in a simple sense, but that our ordinary perception fundamentally misunderstands what reality is. We see separation, multiplicity, individual objects and selves, but the deeper truth is unity, a single consciousness dreaming the many. This is not exactly the simulation hypothesis, but it shares the intuition that surface appearances hide a more fundamental nature of existence. The brain in a vat thought experiment brings these ancient ideas into modern form, imagining a brain removed from a body and kept alive in a laboratory. Scientists stimulate this brain with electrical signals, creating the complete illusion of a body, a world, an entire life. The brain in the vat would have experiences indistinguishable from reality, never suspecting that its perceptions were manufactured by external machines. We cannot prove we are not brains in vats, because any evidence we gather comes through the same possibly deceived senses. These philosophical traditions share a common insight that the evidence of our senses cannot prove the nature of ultimate reality. We assume that seeing is believing, that our experiences represent truth, but each of these arguments shows how that assumption could be wrong. The simulation hypothesis inherits this philosophical legacy, adding the modern twist that computers could be the source of illusion. What ancient philosophers imagined as demons or dreams, we now imagine as software running on unimaginably powerful hardware. The persistence of these questions across cultures and centuries suggests something important, that humans have always sensed something puzzling about the nature of experience. We take reality for granted most of the time, but philosophical reflection reveals how strange it is that anything exists at all. The simulation hypothesis is not a break from tradition, but a continuation, another attempt to understand the mystery that has captivated minds for millennia. Ancient wisdom prepared the ground for modern speculation, showing that questioning reality is a fundamental human activity. There is something peaceful about joining this ancient conversation, becoming part of a tradition of wonder that stretches back thousands of years. The questions we explore tonight have occupied the greatest minds in history, and they remain open despite all our progress and knowledge. We do not need to solve these puzzles to appreciate them. The contemplation itself is valuable, regardless of whether we reach conclusions. Philosophy teaches us to hold questions gently, without demanding answers that may be beyond human reach. As we prepare to examine the modern simulation argument in detail, we carry forward the insights of these ancient thinkers and dreamers. They showed us that reality is not self-evident, that appearances can deceive even the most careful observer. They gave us the conceptual tools to take seriously the possibility that the world is not what it seems. And they demonstrated that such questions, far from being troubling, can be approached with wonder and even tranquility. In the year 2003, a philosopher named Nick Bostrom published a paper that would spark worldwide discussion about the nature of reality. Bostrom, working at Oxford University, did not merely speculate about simulations. He constructed a rigorous, logical argument that demanded serious consideration. His paper, titled "Are You Living in a Computer Simulation?", presented a trilemma, 3 possibilities, of which at least one must be true. Tonight we explore this argument carefully, understanding the logic that has convinced many minds to take simulation seriously. The simulation argument begins with an assumption about the future, that advanced civilizations might develop the capability to run detailed simulations of conscious beings. This is not a certainty, but it seems plausible. Given technological trends, computers have grown exponentially more powerful, and this growth might continue. If a civilization could simulate billions of conscious minds running realistic histories of their ancestors or other conscious beings, then we must ask, what would the statistical consequences of such capability be? Here is where the argument becomes surprising and somewhat disturbing. If advanced civilizations run many ancestor simulations containing conscious beings, and if each simulation might contain billions of conscious minds, then simulated minds could outnumber original minds by an enormous factor. A randomly selected conscious experience would almost certainly be simulated, simply because there would be vastly more simulated experiences than original ones. If you do not know whether you are simulated or original, probability suggests you should bet on being simulated rather than real. Bostrom presents this reasoning as a trilemma with 3 possible conclusions, and he argues that at least one of them must be true. The first possibility is that civilizations almost never reach simulation capability. Perhaps they destroy themselves first, or encounter insurmountable technical barriers. If advanced technology is extremely rare or impossible, then we probably are not simulated because no one is around to simulate us. This would be somewhat reassuring about our reality, but discouraging about the future of technological civilization. The second possibility is that advanced civilizations choose not to run ancestor simulations, even though they have the capability to do so. Perhaps they consider it unethical to create conscious beings in artificial worlds, or they simply have no interest in simulating their ancestors. If all or nearly all advanced civilizations make this choice, then, despite the technological possibility, simulations would be rare. This would also suggest we are probably not simulated, but it requires that this ethical or cultural stance be nearly universal. The third possibility is the most unsettling for our sense of reality, that we almost certainly are living in a computer simulation. If civilizations reach simulation capability and choose to use it, then simulated minds would vastly outnumber original minds. Given no way to know which category we belong to, we should conclude we are probably simulated based purely on the numbers. Bostrom does not claim to know which possibility is true, only that the logic compels us to accept one of these three options. The mathematical reasoning behind the argument involves probability and counting, considering how many original minds versus simulated minds might exist. If even 1% of advanced civilizations run ancestor simulations, and if each simulation contains billions of conscious beings, then the ratio of simulated to original minds could be millions to one, making it statistically almost certain that any random mind is simulated. The math is straightforward once you accept the initial assumptions, and that straightforwardness is part of what makes the argument compelling and troubling. Many people react to the simulation argument with intuitive rejection, feeling that they simply know they are real and not simulated. But this intuition is precisely what the argument challenges. How would a simulated being know it was simulated if the simulation is good enough, indistinguishable from reality? The simulated being would feel just as real as we feel. Our sense of being genuine proves nothing, because that sense would be generated by the simulation along with everything else. The feeling of reality is not evidence of base reality. Bostrom's argument has been debated extensively since its publication, with philosophers and scientists offering both support and criticism. Some have tried to show that the three options are not exhaustive, that there are other possibilities Bostrom did not consider. Others have questioned the assumption that simulated beings would be conscious, arguing that computation alone cannot produce genuine awareness. Still others accept the argument and its conclusion, taking seriously the possibility that we are living in a simulation. One important aspect of the argument is its agnosticism about which possibility is true. Bostrom does not claim to know that we are simulated. He only claims that the logic forces us to accept one of three conclusions, and that we cannot rule out the simulation possibility on the current evidence. This is more modest than it might seem. He is not asserting we are simulated, but showing why we cannot confidently assert we are not. The argument functions as a challenge to our assumptions, not a proof of any particular worldview. The simulation argument has implications that reach beyond academic philosophy, touching on questions about technology, ethics, and the future of civilization. If we take it seriously, we might reconsider what kinds of simulations we create, wondering about the moral status of increasingly realistic virtual beings. We might think differently about artificial intelligence, asking whether our creations might deserve moral consideration. The argument is not just about whether we are simulated, but about what consciousness and reality fundamentally are. For tonight, we do not need to decide whether the simulation argument is sound. We can simply appreciate the strange landscape it opens for exploration. The idea that logic alone might reveal deep truths about reality is part of philosophy's ancient appeal and modern relevance. Whether Bostrom is right or wrong, his argument shows how unexpected conclusions can follow from seemingly innocent premises. This is the adventure of thinking carefully, following ideas wherever they lead, even to surprising destinations. As we continue our journey, we will examine the premises of this argument more closely, asking whether the computing power required is actually achievable. We will look at evidence that might support or undermine the simulation hypothesis, and consider what implications would follow if it were true. But for now, rest with the structure of the argument itself, the elegant trilemma that has sparked so much discussion and debate. The simulation argument assumes that advanced civilizations could simulate conscious beings, but how plausible is this assumption when we consider the actual requirements? Tonight we explore the computing power question, asking whether any computer could ever be powerful enough to simulate an entire universe. This is where philosophy meets physics and computer science, and where the practical limits of technology become relevant. The answer is not as clear as you might expect, and the possibilities remain genuinely open. Let us begin by considering what would need to be simulated, the sheer amount of information contained in the observable universe. There are roughly 10 to the 80th atoms in the observable universe, an almost incomprehensible number that dwarfs human intuition. Each atom has properties like position, momentum, and quantum state, requiring additional information to fully describe its condition. Simulating the entire universe at atomic resolution would seem to require more computing power than could possibly exist. But here is where things become more interesting. A simulation might not need to model every atom with perfect precision. Just as video games render only what the player can see, a simulation might compute only what observers are actually observing. The vast empty spaces between galaxies might be simplified approximations, requiring far less computing power than a full atomic simulation. The simulator might only need to generate detail where conscious beings are looking, producing reality on demand, rather than maintaining it everywhere constantly. This approach is sometimes called a lazy simulation, computing the minimum necessary to maintain the illusion for observers. When you look at the moon, the simulation generates lunar detail, but when no one observes it, the moon might be a simplified placeholder. This sounds strange, but it would dramatically reduce computing requirements. And interestingly, quantum mechanics behaves somewhat like this, with its observer-dependent effects. We will explore this quantum connection later. For now, just note that shortcuts might make simulation far more feasible. Moore's law has described the exponential growth of computing power since the 1960s, with the number of transistors on chips doubling roughly every 2 years. If this trend continued for centuries or millennia, the computing power available would be astronomically greater than today. Even if Moore's law eventually slows, as it seems to be doing, other technologies might continue the exponential growth of computation. Quantum computers, optical computers, or entirely new paradigms might extend computing power far beyond current imagining. Quantum computers deserve special mention because they process information fundamentally differently, using quantum bits or qubits that can represent multiple states simultaneously. A quantum computer with a few hundred qubits could solve problems that would take classical computers longer than the age of the universe. If our simulators have mastered quantum computation, they might wield processing power that we cannot even conceptualize properly. The limits we see from our current technological position might be nothing like the limits facing an advanced civilization. Some researchers have tried to estimate the minimum computing requirements for simulating reality, using physics to calculate how much information the universe contains. These estimates vary widely depending on assumptions, from barely possible with foreseeable technology to utterly impossible by any means. The uncertainty itself is significant. We cannot confidently say whether simulation is feasible or not. The question remains genuinely open, neither clearly possible nor clearly impossible. Another consideration is that our physics might not be the simulator's physics. The rules we discover might be just the rules of our simulated environment. The base reality, running our simulation, might have different physical laws, perhaps allowing computing capabilities that would be impossible under our physics. We cannot use our physics to limit what the simulators can do, because they exist outside our physics, in a reality we cannot observe. This makes the computing power question even more difficult. Our limits might not be their limits. The consciousness question is perhaps even more fundamental than computing power. Can awareness be created through information processing at all? Some philosophers argue that consciousness is irreducible, that no amount of computation could ever produce genuine subjective experience. If this is true, then simulations might create complex behaviors without creating minds, philosophical zombies that act conscious without being conscious. The simulated beings would not actually experience anything, and the moral implications of the simulation hypothesis would be very different. Others argue that consciousness is purely computational, that awareness emerges from information processing regardless of the substrate. If your brain is essentially an information processing system, then simulating that processing exactly would create genuine consciousness. The simulated mind would experience, think, feel as genuinely as any biological mind, despite being made of different stuff. This view, called functionalism, makes consciousness substrate independent and makes simulated consciousness theoretically possible. The debate between these positions remains unresolved in philosophy of mind, and we cannot know for certain whether computed consciousness is possible. If it is impossible, then the simulation argument fails at this step. No matter how much computing power exists, conscious simulations could not be created. But if it is possible, then the computing power question becomes central, and the exponential growth of technology becomes relevant to our reality. We cannot resolve this tonight, but we can appreciate the stakes. Our understanding of consciousness determines whether simulation is even conceivable. For the purposes of our journey tonight, we leave this question open, acknowledging both the possibilities and the uncertainties. Computing power is growing, and we cannot set firm limits on how far it might go, just as people a century ago could not imagine today's computers. Consciousness might or might not be computable, and until we understand awareness better, we cannot rule out either option. The simulation hypothesis lives in this space of genuine uncertainty, where neither confident assertion nor confident denial is fully justified. What is clear is that dismissing the simulation hypothesis as impossible is not warranted. The objections based on computing power are not as decisive as they first appear. Advanced civilizations might find shortcuts, harness quantum effects, or discover new physics, possibilities that make our current limits irrelevant. We should hold the question with appropriate humility, recognizing that we are early in our technological journey and cannot foresee its limits. If we are living in a simulation, might there be evidence of this hidden in plain sight, clues written into the fabric of reality that reveal its computational nature? Tonight we explore the features of our universe that some find suggestive of simulation, the mathematical structure of physics, the digital nature of quantum mechanics, the suspicious precision of constants. These observations do not prove we are simulated, but they provide intriguing hints that make the hypothesis seem less absurd. Let us examine this evidence with curiosity and appropriate skepticism. The most striking feature of our universe is how perfectly it obeys mathematical laws, the equations of physics describing reality with extraordinary precision. This is so familiar that we rarely pause to wonder at it, but why should the universe follow mathematics so faithfully? Matter obeys differential equations, particles follow symmetry principles, forces decrease with the square of distance, not some arbitrary power. The physicist Eugene Wigner wrote a famous essay on this puzzle, calling it the unreasonable effectiveness of mathematics in the natural sciences. If the universe is a simulation, this mathematical perfection becomes less mysterious because simulations are built from mathematical rules and algorithms. A programmer creates a physics engine by writing equations, and the simulated world obeys those equations perfectly, because that is all it is. The laws of physics would be lines of code, and their mathematical beauty would reflect the elegance of the underlying program. This does not prove simulation, but it provides a natural explanation for why reality seems so suspiciously mathematical. Digital physics is a field that takes this idea further, proposing that the universe is fundamentally informational at its deepest level. In this view, physical reality is not made of stuff, but of data, bits of information that combine according to computational rules. Particles, forces, space, and time would all be patterns of information, like pixels on a cosmic screen, that display the appearance of reality. This is a minority view among physicists, but it is taken seriously by some respected researchers. The speed of light might be interpreted as a processing limit, the maximum rate at which information can propagate through the simulation. Just as video games have maximum speeds for objects, the universe might impose a speed limit based on computational constraints. Nothing can travel faster than light in our universe, and this could reflect the clock speed of the cosmic computer. This is speculative, but it shows how simulation thinking can reframe familiar physical facts in suggestive ways. The Planck length is the smallest meaningful distance in physics, about 10 to the minus 35 meters, unimaginably tiny. Below this scale, our current physics breaks down, and some theorists suggest this represents the pixel size of reality. Just as a computer screen has limited resolution, the universe might have a fundamental granularity that sets minimum sizes and times. If reality is computed, you would expect such discreteness, because computers work with discrete values rather than truly continuous quantities. Quantum mechanics is especially suggestive from a simulation perspective, because quantum behavior resembles computation optimization in strange ways. Particles exist in superpositions of states until measured, as if the simulation is not deciding their properties until forced to. This is eerily similar to lazy computation, rendering details only when observed, saving processing power. The observer effect, where measurement affects outcomes, might be the simulation generating reality in response to observation. The double-slit experiment is the iconic example of this quantum strangeness, where particles seem to take all possible paths until observed. When not observed, particles pass through both slits simultaneously, creating interference patterns that reveal their wave-like nature. But when observed, the interference vanishes, and particles behave like classical objects, taking definite paths. This dependence on observation is exactly what you would expect if the simulation computes detail only when necessary for observers. Quantum entanglement provides another suggestive feature, where particles remain connected regardless of the distance between them. Measuring one entangled particle instantly affects its partner, even if they are on opposite sides of the universe. This violates our intuitions about locality and causality, but might make sense if both particles are entries in the same database program. In a simulation, distance is just a number, and updating correlated data entries requires no physical travel. The fine-tuning of universal constants, which we will explore more fully later, also seems suggestive of deliberate design, rather than random chance. The numbers governing physics seem precisely set to allow complexity and life, as if someone adjusted the parameters for this purpose. This could be evidence of simulation. The programmers chose constants that would produce interesting results. Or it could have other explanations, but the suspicious perfection deserves our attention. We should be careful not to overinterpret these observations. Each has alternative explanations that do not require simulation. The mathematical nature of physics might just be a brute fact, the way reality happens to be without deeper explanation. Quantum strangeness might reflect our incomplete understanding, rather than evidence of computation. Fine-tuning might be explained by the multiverse or anthropic reasoning, without invoking simulation as the cause. The evidence is suggestive, but not conclusive. What these observations do establish is that simulation is not absurd. The universe has features consistent with being computed, even if this is not proven. The mathematical precision, the quantum observer effects, the apparent limits and granularity all make simulation at least possible to take seriously. We cannot look at the universe and say definitively it is not simulated, because what we see is compatible with the simulation hypothesis. This is enough to make the question worth exploring, even if it does not settle the answer one way or the other. As you rest with these suggestive observations, let them spark curiosity rather than conclusions. The universe is strange and wonderful, and its strangeness might or might not point towards simulation. We explore these ideas not to reach certainty, but to appreciate the mystery that surrounds us. Quantum mechanics is the most successful theory in the history of physics, yet it describes a reality so strange that even experts struggle to understand it. Particles exist in multiple states at once. Observation changes outcomes. Entanglement connects distant objects in ways that seem impossible. Tonight we explore how quantum strangeness might relate to the simulation hypothesis, asking whether these bizarre features could be clues about the nature of reality. The connections are speculative but fascinating, and they reveal how deep the mystery of quantum mechanics truly is. At the quantum level, particles do not have definite properties until measured. They exist in superpositions of all possible states simultaneously. An electron does not have a specific position until you look for it. It has a cloud of possible positions described by probability. This is not just ignorance about where it is. The electron genuinely is in multiple places at once until observation collapses the superposition. This behavior has been confirmed by countless experiments, and it remains one of the most puzzling aspects of reality. The simulation perspective offers an interesting interpretation of superposition. The particle's properties are not calculated until something requires them. Just as a video game does not render what the player cannot see, the simulation might not compute particle positions until measurement demands it. Superposition would be the uncomputed state, a placeholder that becomes definite only when observation forces resolution. This would be efficient programming, avoiding unnecessary calculation for properties no one needs to know. The famous double-slit experiment illustrates this quantum behavior vividly, showing how particles can behave like waves when not observed. When electrons are fired at a barrier with two slits, they create an interference pattern on the detector behind, suggesting wave behavior. But this only happens when we do not track which slit each electron passes through. If we observe the path, the interference vanishes and electrons behave like particles. The act of observation changes the physical outcome, as if the universe responds to what we are paying attention to. From a simulation perspective, this observer effect is natural. The program generates particle behavior only when observers require definite trajectories. When no observer tracks the path, the simulation can use efficient wave calculations, but observation forces the rendering of specific particle positions. This is exactly how a well-designed simulation might work, optimizing resources by computing only what is necessary. The strangeness of quantum mechanics might be the signature of computational efficiency in the underlying program. Quantum entanglement adds another layer of suggestive strangeness, where particles become linked in ways that transcend ordinary space. When two particles are entangled, measuring one instantly affects the other, regardless of the distance separating them, even light years apart. This seems to violate relativity's speed limit for information, yet the correlations are real and have been experimentally verified. Einstein called this spooky action at a distance, and never fully accepted its implications for the nature of reality. In a simulation, entanglement becomes much less mysterious. The connected particles are just entries in the same database. When one entry is accessed and updated, the correlated entry updates too, not through any physical signal, but through shared reference in the program. Distance is just a number in the simulation, and updating related data requires no travel through space. What seems like magic in physical reality becomes ordinary programming from the perspective of the simulator. The measurement problem is the deep puzzle at the heart of quantum mechanics. Why does observation cause the wave function to collapse? The equations of quantum mechanics describe smooth, deterministic evolution until measurement abruptly forces a random outcome from among possibilities. What counts as a measurement? What exactly triggers the collapse? These questions remain controversial among physicists. After a century of debate, different interpretations of quantum mechanics offer different answers, none of them fully satisfying. The simulation interpretation offers a perspective on this puzzle. Measurement is the moment when the program must provide a definite output. Until something in the simulation requires specific data, the system can maintain efficient superpositions of possibilities. But when an observation occurs, the simulation must choose, rendering a specific outcome from the probability distribution. This does not fully solve the measurement problem, but it provides a framework for understanding why measurement might be special. Some physicists have proposed that quantum mechanics itself might be evidence of simulation, that no physical reality could behave this way. The alternatives, like the many worlds interpretation with its infinite branching universes, seem almost as strange as the simulation hypothesis itself. Perhaps quantum mechanics seems paradoxical because we expect physical intuitions to apply. But our reality is actually computational, operating by different rules than we assume. This is speculation, not proof, but it shows how quantum weirdness opens doors to unconventional thinking. The physicist John Wheeler proposed a related idea with his it-from-bit hypothesis, suggesting that all physical existence derives from information. Wheeler imagined that every particle, every field, every aspect of reality ultimately arises from yes-no questions, from bits of information. This is not exactly the simulation hypothesis, but it moves in the same direction, seeing reality as fundamentally informational. If Wheeler was right, the universe is already computational in its essence, making the idea of simulation seem more natural. We should be careful not to conclude too much from these quantum considerations. They are suggestive, but not conclusive evidence of simulation. Quantum mechanics might simply describe how physical reality works, strange as that reality is, without requiring a simulation explanation. The observer effect might have explanations we have not yet discovered, interpretations that do not involve computation or simulation at all. We remain in the realm of speculation, intrigued by possibilities but not certain of conclusions. What quantum mechanics teaches us, regardless of simulation, is that reality is far stranger than common sense suggests. The universe at its deepest level does not behave like everyday objects. It follows rules that violate our intuitions about how things should work. This strangeness makes it harder to dismiss unusual ideas like simulation, because we already know that reality is weird. The quantum world has taught us humility about what we can and cannot assume about the nature of existence. The universe seems suspiciously well adjusted for the existence of life and consciousness, as if someone had carefully chosen the numbers governing physics. The physical constants, the forces and masses and ratios all appear fine-tuned to allow complexity, chemistry, stars, and ultimately us. Tonight we explore this fine-tuning puzzle, asking whether it might be evidence that our universe was deliberately designed. This does not prove simulation, but it adds another layer to the mystery of why reality is as it is. Consider the cosmological constant, the energy density of empty space, a number that determines whether the universe expands, contracts, or remains stable. If this constant were slightly larger, the universe would have expanded too fast. Galaxies and stars would never have formed from the primordial gas. If it were slightly smaller, the universe might have recollapsed, crushed back into oblivion before life could evolve. The actual value seems balanced on a knife edge, precisely the tiny number needed for the universe we observe. The strength of the strong nuclear force shows similar fine-tuning, binding protons and neutrons together in atomic nuclei. If this force were just a few % stronger, hydrogen would be unstable, and the universe would contain almost no hydrogen, the fuel of stars. If it were a few % weaker, atomic nuclei could not form, and no elements beyond hydrogen would exist. Chemistry and biology would be impossible either way, yet the actual value allows for the rich chemistry that makes life possible. The ratio of electron mass to proton mass also seems finely balanced, affecting the structure of atoms and the behavior of molecules. If electrons were much heavier, atoms would be different. Chemistry would not produce the complex molecules needed for biology. If they were much lighter, different problems would arise, and again, life as we know it would be impossible to form. The actual ratio produces stable atoms and complex chemistry, as if chosen to enable the conditions for consciousness. These are just a few examples among many. Physicists have identified dozens of apparent fine-tunings in fundamental physics. The gravitational constant, the electromagnetic force, particle masses, and charges all seem precisely set to allow the universe to be interesting. Change any of them slightly, and you get a boring universe, one without stars, without chemistry, without the complexity needed for life. The actual values seem special, picked from an enormous range of possibilities to produce exactly what we observe. Why should the constants have these life-permitting values? And what explanation could account for such apparent precision? There are several possible answers, none of them fully satisfying, and the simulation hypothesis is one among these competing explanations. Each approach has strengths and weaknesses, and the mystery of fine-tuning remains genuinely open. The design hypothesis suggests that an intelligent creator chose the constants, deliberately setting the parameters to produce life and consciousness. This is the religious answer, aligning with beliefs about divine creation, and fine-tuning has been used as evidence for God by some theologians. The simulation hypothesis is a secular version of this idea, replacing God with programmers who designed our universe for their purposes. Both suggest deliberate choice behind the apparent precision, rather than chance or necessity. The anthropic principle offers a different perspective, noting that we can only observe universes capable of producing observers. If the constants were different and life were impossible, no one would be around to notice the inhospitable conditions. We necessarily find ourselves in a universe where life is possible because we could not exist anywhere else to ask the question. This does not explain why such a universe exists, but it explains why we observe one that seems fine-tuned. The multiverse hypothesis extends the anthropic reasoning, proposing that countless universes exist with different constants. In most universes, the constants do not permit complexity, but in a few, by chance, the numbers align for life to develop. We necessarily find ourselves in one of these rare, life-permitting universes, simply because we could not exist in the others to wonder about fine-tuning. This removes the need for deliberate design, replacing it with random variation across infinite possibilities. The simulation hypothesis offers yet another explanation. The constants are chosen because the simulators wanted a universe with life. Perhaps they are running an experiment in consciousness, or studying how intelligent beings develop under particular physical conditions. Perhaps our universe is entertainment, a game, an art project, or something we cannot imagine from inside the simulation. Whatever their purpose, the simulators selected constants that produce observers, and fine-tuning is evidence of their intentional design. What makes fine-tuning significant for our inquiry tonight is that it shows the universe is special in ways that demand explanation. The constants could have been anything, but they have specific life-permitting values, and this requires some account, whether divine, anthropic, multiverse, or simulation. We cannot simply shrug and say the numbers are what they are. The precision calls out for understanding, even if we cannot achieve certainty. Fine-tuning is evidence that something interesting is going on, something that makes simulation seem less far-fetched as an explanation. None of these explanations can currently be proven or definitively ruled out. We are in the realm of metaphysics, where evidence is sparse. But the simulation hypothesis holds its own among the competitors, no more absurd than divine creation or infinite multiverses. The fine-tuning of the universe remains a genuine puzzle, and simulation is a genuine contender for solving it. This does not mean simulation is true, only that it deserves consideration alongside other approaches. Popular culture imagines that simulated realities might contain glitches, errors in the program that reveal its artificial nature. Tonight, we explore strange phenomena that some people interpret as evidence of simulation: the Mandela effect, déjà vu, synchronicities, and other puzzling experiences. We will examine these with curiosity and appropriate skepticism, appreciating the wonder while acknowledging what science actually explains. These experiences are fascinating, whether or not they indicate simulation, and they reveal how strange ordinary consciousness actually is. The Mandela effect refers to widespread shared false memories, large numbers of people remembering events differently than they actually occurred. The name comes from people who recall Nelson Mandela dying in prison in the 1980s, when in fact he was released and lived until 2013. Similar examples include memories of movie lines, book titles, and brand names that differ from the documented reality in consistent ways. How could so many people share the same false memory, unless something strange is happening to reality itself? The simulation interpretation suggests these might be edits to the program, changes made by the simulators that most people do not notice, but some remember the previous version. Perhaps the simulators corrected an error or made an update, and most memories were adjusted to match, but some slipped through. This would explain shared false memories as glimpses of earlier versions, glitches in the memory editing process. It is an intriguing idea, but the evidence does not really support it. The psychological explanation for the Mandela effect is more mundane but also fascinating, revealing how unreliable human memory actually is. Memory is not a video recording, but a reconstruction. Each recall rebuilds the memory from fragments, influenced by expectations and suggestions. When many people have similar expectations, they can independently construct similar false memories without any external cause. The Mandela effect demonstrates the fallibility of memory, not glitches in reality, but glitches in human cognition. Déjà vu is the eerie sensation that you have experienced the present moment before, a feeling of familiarity that seems impossible to explain. Nearly everyone has experienced déjà vu at some point. The sudden conviction that this conversation, this room, this exact situation has happened before. The experience can be so vivid and convincing that it seems like evidence of something strange about time or reality. Some interpret it as a glitch in the simulation, a moment of repetition or faulty memory loading. Neuroscience offers more prosaic but equally interesting explanations for déjà vu, involving how the brain processes familiarity and novelty signals. Sometimes the brain incorrectly flags a new experience as familiar, perhaps due to timing mismatches between different memory systems. The feeling of having been here before is genuine, but it reflects a neural error rather than an actual repetition. This does not make déjà vu less interesting, but it suggests the glitch is in our brains rather than in reality. Synchronicity is the term Carl Jung used for meaningful coincidences, events that seem too perfect to be random but have no causal connection. You think of a friend and immediately they call, you notice a word and suddenly see it everywhere. These experiences feel significant, as if the universe is sending messages or as if reality is responding to your attention in uncanny ways. Some interpret synchronicities as evidence that reality is not as random as it seems, perhaps programmed to create meaning for observers. The statistical explanation for synchronicity involves probability and cognitive bias, our tendency to notice hits and forget the many misses. You think of friends hundreds of times without them calling and forget all those non-events while remembering the one coincidence. The human brain is wired to find patterns, and we often discover meaning where none was intended. This does not diminish the subjective significance of synchronicities, but it suggests they reveal more about minds than about simulated reality. Near-death experiences have been reported by people who came close to dying, often describing tunnels of light encounters with deceased relatives and feelings of peace. Some experiencers report observing their own bodies from above, or gaining knowledge they could not have obtained through normal means. These experiences feel profoundly real to those who have them, and some interpret them as glimpses beyond the simulation, moments of awareness outside the program. The neuroscience of near-death experiences is still being researched, but many elements can be explained by brain activity during oxygen deprivation. The tunnel of light may result from how the visual cortex shuts down, and feelings of peace may reflect neurotransmitter floods during trauma. Out-of-body experiences can be induced artificially, suggesting they are brain phenomena rather than evidence of soul departure. This does not prove the experiences are not genuine glimpses beyond reality, but it provides alternative explanations that do not require simulation. The human tendency to see glitches in reality might itself be revealing, showing how our minds construct experience from incomplete information. Every perception is an interpretation, a model built by the brain, not a direct window onto external reality. When this model glitches through memory errors, timing problems, or pattern seeking, we experience strangeness that feels like evidence of something deeper. But the strangeness is in us, in how we process the world, not necessarily in the world itself being simulated. This does not mean we should dismiss all strange experiences as neural errors. Genuine mysteries remain that science has not fully explained. Consciousness itself is perhaps the deepest mystery. How physical brains produce subjective experience remains utterly unknown. The hard problem of consciousness resists scientific explanation, and perhaps this resistance is a clue that something is fundamentally different than we assume. We should remain humble about what we think we know, open to possibilities while skeptical of easy answers. If we are living in a simulation, perhaps the most intriguing question is, who created it? And what purpose could possibly justify simulating billions of conscious beings? Tonight we explore the possible motivations of hypothetical simulators, the reasons they might have for creating a universe like ours. This is necessarily speculative, but the speculation reveals something about what we value and what we imagine advanced intelligences might value. The question of purpose shapes how we might feel about being simulated. The most discussed possibility is ancestor simulations, future humans or their descendants running detailed simulations of their past. They might want to understand how history unfolded, experiencing firsthand the events and decisions that shaped their civilization. We already create historical documentaries, reenactments, and video games. Ancestor simulations would be the ultimate extension of this historical interest. If understanding the past is valuable to future beings, They might create countless simulations of different historical periods and paths. Scientific research might motivate simulations of entire universes, testing hypotheses about how civilizations develop under various conditions. Perhaps the simulators want to understand consciousness, studying how awareness emerges in different types of beings and circumstances. Or they might be exploring sociology, economics, or political science, observing how societies form, grow, and sometimes collapse. A simulated universe would be the ultimate laboratory, allowing experiments impossible to conduct in base reality. Entertainment is a less flattering but plausible motivation. Our universe as a game or drama for beings who enjoy watching or participating. We already create games with simulated beings, characters in video games that pursue goals and face challenges. Advanced entertainment might involve fully conscious simulated beings whose experiences are real to them, even if observed as drama by outsiders. The ethics of this are troubling, but we cannot assume simulators share our moral intuitions. Educational simulations might serve to teach young beings about history or ethics, immersive experiences that develop wisdom through simulated choices. Perhaps children in the base reality learn compassion by experiencing simulated lives, understanding suffering and joy through direct, if artificial, experience. This would give our lives meaning as teaching tools, our struggles and triumphs serving to educate beings we will never meet. It is a strange purpose, but not without a kind of value. Nested simulations raise the possibility of simulations within simulations, an endless hierarchy of created universes. If our simulators are themselves simulated, then the question of purpose becomes even more complex and recursive. There might be no original base reality at all, just simulations all the way down, each creating the next. This seems paradoxical, requiring something to start the chain. But perhaps our intuitions about infinite regress are wrong. The simulators might have purposes we cannot comprehend at all, motivations as alien to us as ours are to ants or bacteria. We imagine human-like curiosity, entertainment, science, and education, but advanced beings might have values entirely different from anything we can conceive. Perhaps creating universes is art, religion, procreation, or something with no human analogue, a form of existence we lack the concepts to understand. The gulf between us and our hypothetical creators might be greater than we can imagine. One possibility is that we are not the point at all, that conscious beings like us are incidental byproducts of a simulation run for other purposes. Perhaps the simulators are studying physics, testing mathematical structures, and consciousness emerged accidentally in their calculations. We might be unintended, unexpected, possibly even unnoticed by our creators. This is humbling, but also strangely liberating. We would owe nothing to creators who do not know we exist. The question of whether the simulators intervene in our reality is also interesting. Do they watch, adjust, reset, or simply let the simulation run? Miracles, answered prayers, and strange coincidences might be interventions, or they might be programmed features rather than active meddling. Perhaps the simulators set initial conditions and let physics take over, or perhaps they are constantly tweaking to achieve desired outcomes. We have no way to know from inside. Any intervention would appear as natural events to us. The purpose question matters because it affects how we should feel about being simulated, whether we should feel used or valued, observed or ignored. If we are ancestor simulations, Our creators care about understanding us. Our lives have meaning as connections to their heritage. If we are experiments, our experiences generate valuable knowledge, contributing to understanding that transcends our individual existence. If we are entertainment, our struggles are at least witnessed and appreciated, even if the appreciation comes from beings we will never meet. Perhaps the most comforting possibility is that the simulators value consciousness itself, creating aware beings, because awareness is inherently precious. They might believe that more consciousness is better, and by creating simulated minds, they are multiplying the good of experience in existence. Our joys and discoveries would have value to our creators, not as data or entertainment, but as goods in themselves. This would make us ends rather than means, valued for our own sake rather than for what we provide. We cannot know the true purpose, if any, behind our possible simulation, but contemplating possibilities helps us think about what gives life meaning. If our existence has purpose beyond ourselves, that might be comforting or disturbing depending on the purpose. If it has no external purpose, then we must find meaning within our own experience, as we would anyway. The purpose question is fascinating, but it may not change how we should live our lives. We've explored many reasons to take the simulation hypothesis seriously. Now let us honestly examine the arguments against it. Good thinking requires considering objections, and the simulation hypothesis faces significant challenges that deserve attention. Tonight, we explore why many scientists and philosophers remain skeptical, and why the simulation might be far less likely than some enthusiasts claim. Understanding these objections deepens our appreciation of the question. The most fundamental objection concerns falsifiability, the principle that scientific hypotheses should be testable in ways that could prove them wrong. If we are in a simulation, what observation could ever reveal this? What experiment could distinguish simulated physics from real physics? Anything we observe was generated by the simulation, so we cannot step outside to check whether an external reality exists. A hypothesis that cannot be tested is not science, but metaphysics, beyond the reach of empirical investigation. Some defenders of the hypothesis propose potential tests looking for computational artifacts, limits, or inconsistencies in physical laws. But even if we found such anomalies, simulation would be only one of many possible explanations. And if we found no anomalies, that would not disprove simulation, because a well-designed simulation might be perfectly consistent. The hypothesis seems to explain anything and predict nothing specific, which makes it unfalsifiable in the technical sense. Occam's razor is a principle that favors simpler explanations over more complex ones, and simulation might seem to multiply entities beyond necessity. Why postulate simulators, base reality, and computing substrate when we could simply accept that physical reality is fundamental? The simulation hypothesis does not explain existence. It pushes the question back a level, requiring explanation for the simulators. If base reality can exist without explanation, perhaps our reality can too, making simulation an unnecessary complication. However, defenders note that Occam's razor favors simplicity of principles, not entities. And the simulation hypothesis might actually simplify by explaining fine-tuning and other puzzles. If simulation explains multiple mysteries with one principle, it might be simpler overall, despite postulating additional entities. The debate about simplicity is not straightforward, and neither side has a decisive advantage on this ground. While the simulation hypothesis captures imagination and sparks fascinating debates, many scientists and philosophers have raised serious objections to the idea. These arguments deserve careful consideration alongside the evidence that seems to support simulation, because intellectual honesty requires us to examine both sides of any question. Tonight, we explore the reasons why many thinkers remain skeptical, the challenges that simulation theory faces when subjected to rigorous analysis. Understanding these objections does not diminish the wonder of the question. It deepens our appreciation for how complex the mystery of reality truly is. The most fundamental objection concerns falsifiability, the criterion that separates science from speculation, and whether the simulation hypothesis can ever be tested in any meaningful way. A scientific theory must make predictions that could, in principle, be proven wrong. Otherwise, it remains a philosophical idea rather than a scientific claim. If the simulation hypothesis cannot be falsified by any possible observation, then it occupies a strange territory outside of what science can address. This does not mean it is false, only that science may not be the right tool for evaluating it. The challenge is that any evidence we might find could be explained either way. Glitches could be natural phenomena we do not yet understand, or actual errors in simulation. The mathematical nature of physics could reflect deep truths about reality, or could indicate that reality is computed using mathematical rules. This flexibility is both the strength and weakness of the simulation hypothesis. It can accommodate almost any observation, which means no observation decisively confirms or refutes it. Critics argue this makes it more like religion than science, a matter of faith rather than evidence. Some researchers have proposed specific tests that might reveal simulation, looking for computational artifacts or limitations in the structure of physics. If the universe is simulated on a discrete lattice, like pixels in a screen, there might be slight anisotropies or directional effects in high-energy cosmic rays. Searches for such effects have been conducted, and so far, nothing conclusive has been found, though absence of evidence is not evidence of absence. The simulators might use techniques that leave no detectable artifacts, or the resolution of the simulation might be far finer than we can probe. Occam's razor presents another challenge to the simulation hypothesis, the principle that simpler explanations should be preferred over more complex ones. Which is simpler, that reality is fundamental and exists on its own, or that reality is computed by another reality that must also be explained? The simulation hypothesis does not eliminate the mystery of existence, it merely pushes that mystery up one level to the simulator's reality. If their reality requires explanation, and their simulator's reality too, we face an infinite regress that explains nothing at all. Some argue that base reality, whatever that means, must exist somewhere in the chain, and the simplest assumption is that our reality is that base level. Adding layers of simulation adds complexity, without adding explanatory power. We still must explain why anything exists at all, simulated or not. The simulation hypothesis might feel like an explanation, but it may simply be relocating the mystery, rather than solving it. Occam's razor suggests we should not multiply entities beyond necessity, and simulators are entities we have no direct evidence for. The consciousness problem poses perhaps the deepest challenge to simulation theory, the question of whether awareness can be computed at all. We do not understand how consciousness arises from physical processes, how subjective experience emerges from neurons firing in brains, If we cannot explain consciousness in terms of known physics, how can we assume it would emerge from computations in a simulation? This is the hard problem of consciousness, and it remains unsolved regardless of whether we are simulated. Some philosophers argue that consciousness might be non-computable, that awareness involves something beyond information processing. If this is true, then simulating conscious beings might be fundamentally impossible, no matter how powerful the computer running the simulation. We might simulate behavior that mimics consciousness, but the inner experience of being aware might require something simulations cannot provide. This objection is speculative, since we do not know what consciousness requires, but it highlights the enormous assumptions built into the simulation hypothesis. Even if consciousness can arise from computation, we face the question of computational resources, whether any civilization could actually build a universe simulating computer in practice. The observable universe contains roughly 10 to the 80 atoms. Simulating each one would require enormous computational power and memory. Even with optimizations like simulating only what is observed, the requirements might exceed what is physically possible in any reality. There may be fundamental limits on computation that no civilization can transcend, laws of physics that apply even to the simulators themselves. The physicist Seth Lloyd has calculated limits on how much computation the universe could perform, based on the total energy available and the time since the Big Bang. These calculations suggest that simulating a universe as complex as ours might require resources approaching the scale of an entire universe itself. This makes ancestor simulations less plausible than they initially seem, because each simulation would need nearly as much space and energy as the reality being simulated. The easy assumption that advanced civilizations could create countless simulations may underestimate the fundamental constraints on computation. The recursion problem extends this concern to nested simulations, the idea of simulations within simulations within simulations, layers deep. If we are in a simulation, perhaps our simulators are in one too, and their simulators, and so on, in infinite regression. But each level of simulation might require resources from the level above, and computational losses at each level would quickly make deep nesting impossible. There may be limits on how many levels of simulation can exist, practical constraints that prevent the infinite stacking the hypothesis sometimes imagines. Many scientists remain skeptical simply because the hypothesis is unnecessary. It does not solve any specific problem that physics faces. The simulation hypothesis was not proposed to explain experimental anomalies or to unify theories or predict new phenomena. It is a philosophical speculation that might be true, but does not need to be true. Nothing in our observations requires us to believe we are simulated. Scientists generally prefer theories that are forced by evidence, not theories that are possible, but unmotivated by specific observations. The argument that mathematical physics suggests simulation can be turned around. Perhaps mathematics describes reality well because mathematics is about patterns and reality has patterns. This does not require reality to be computed. It only requires reality to be orderly in ways that mathematics can capture. The effectiveness of mathematics might reflect our evolutionary adaptation. Brains that could recognize patterns survived better than those that could not. We invented mathematics precisely because we live in a patterned universe, not because the universe is running on mathematical code. Similarly, the discreteness of quantum mechanics does not necessarily indicate digital computation. It might reflect fundamental features of nature that have nothing to do with simulation. Quantization was discovered through experiments, not through assumptions about computation. And it may be a deep truth about how reality works at small scales. Just because something reminds us of computers does not mean computers are involved. This is a form of pattern matching that can lead us astray. We should be careful about projecting our technological concepts onto the cosmos. The fine-tuning of physical constants is often cited as evidence for simulation, but there are other explanations that do not require simulators. The multiverse hypothesis suggests that all possible constants are realized somewhere, and we observe our constants because only these values allow observers to exist. This anthropic explanation may be unsatisfying, but it does not require a simulator. Just a vast ensemble of universes with varying properties. Alternatively, future physics might show that the constants are not arbitrary, that they are determined by deeper principles we have not yet discovered. Some physicists believe that a true theory of everything will explain the constants, deriving their values from mathematical necessity rather than tuning. We are far from such a theory, but that does not mean it is impossible. It may simply require centuries more work to uncover. Giving up and attributing the constants to a simulator might be premature surrender rather than the best explanation. Science has solved many mysteries that once seemed to require supernatural explanation, and fine-tuning might eventually yield to similar progress. As you consider these objections, notice that none of them prove we are not in a simulation. They only raise challenges and alternatives to consider. The simulation hypothesis remains a possibility that cannot be ruled out, but it is not the only possibility and may not be the most likely one. Intellectual humility requires holding the question open, not committing too firmly to any answer we cannot verify. Suppose for a moment that the simulation hypothesis is true, that everything you experience is computed by some vast system beyond your perception. What would this mean for your life, your relationships, your sense of purpose? Would it change anything about how you live or what matters to you? Tonight we explore these questions gently, not to disturb your peace, but to discover that meaning persists, regardless of what reality ultimately is. The answer, perhaps surprisingly, is that very little would need to change, and the things that matter would still matter just as much. The first reaction many people have is that simulation would make everything meaningless, that if we are not real, then nothing we do matters. But this reaction deserves examination, because it assumes that simulated beings are somehow less real, less worthy of consideration than beings in base reality. Consider that from your perspective, your experiences are completely genuine. Your joys and sorrows, your loves and fears are real to you regardless of their ultimate substrate. If you feel pain, that pain is real as an experience, whether the neurons causing it are made of atoms or of information. Philosophers call this the substrate independence of experience, the idea that what matters is the pattern of consciousness, not what implements it. If your mind were perfectly copied to a different medium, you would presumably still be you with all your experiences and memories. This suggests that being simulated does not diminish your reality. You are real in the most important sense, as a locus of experience and awareness. The electrons in your brain are already just patterns of energy, and patterns of information might serve the same function. Consider how you think about characters in dreams. While dreaming, they seem completely real to you, and your interactions with them feel meaningful. If you could ask those dream characters whether their experiences matter, they would presumably say yes, even though they exist only in your sleeping mind. Perhaps we are like dream characters in a larger mind, and yet our experiences remain genuine and valuable. The analogy is imperfect but suggestive. Reality is real from the inside, regardless of its ultimate nature. Some people worry that simulation would mean we have no free will, that our choices are determined by the code running the simulation. But this concern applies equally to a non-simulated universe governed by physical laws. If atoms follow deterministic equations, then free will is already challenged. Simulation does not create a new problem for free will. It merely restates the ancient puzzle in new terms. Whether our brains are made of atoms or computations, the question of whether we truly choose remains equally mysterious. In fact, simulation might actually support some forms of free will better than physical determinism if the simulators have introduced randomness or genuine choice points into the program. Perhaps the simulation was designed to create beings with authentic agency, beings whose choices are not fully determined by initial conditions. We cannot know the simulator's design principles, but there is no reason to assume they would eliminate the very freedom that might make simulated beings interesting. If they wanted to study ethics or moral development, they would need beings capable of genuine choice and responsibility. The relationships you have with other people would remain just as meaningful in a simulation, because those other people are having experiences just as real as yours. Your love for family and friends is not diminished by being computed. Love is love, regardless of what underlies the minds that feel it. The connection you feel with others, the shared experiences, the memories you build, these are the substance of meaning, and they persist in any reality. Whether atoms or algorithms implement your relationships, the relationships themselves are what matter. Suffering and joy would retain their full moral weight in a simulated world. Simulated pain hurts just as much as any other kind. This has implications for how the simulators should treat us if they exist. Creating beings capable of suffering carries ethical responsibilities. But it also means that kindness and compassion remain important for us. Reducing suffering is good, regardless of whether reality is fundamental or computed. If anything, believing we are simulated might increase our moral concern, knowing that conscious beings can exist in substrates we once thought inanimate. The search for meaning would continue in a simulated universe, because meaning was never guaranteed by the physical nature of reality anyway. Even in a non-simulated universe of atoms and void, meaning is something we create through our values and our projects. A simulated universe offers the same opportunity to find or create meaning through love, creativity, discovery, and connection. The ultimate nature of reality has never been the source of meaning. Meaning arises from within conscious experience, wherever that experience occurs. Some people find comfort in the simulation hypothesis, the idea that someone created this reality, that it exists for a purpose. Even if we do not know the purpose, there is purpose. Unlike a universe that exists by chance with no reason or intention. This is similar to how some people find comfort in religious belief, the sense that existence is intentional rather than accidental. Whether this comfort is justified depends on assumptions about the simulators, but the feeling of meaning is available to those who find it. Others find the simulation hypothesis disturbing, and that is understandable too. The idea that reality is not what it seems can be unsettling. But remember that reality has never been exactly what it seems. The solid table is mostly empty space. Time flows differently depending on speed. Every advance in physics has revealed that reality is stranger than intuition, and we have adapted to each revelation without losing our sense of meaning. If simulation is true, we will adapt to that understanding too, and life will continue to feel as real and meaningful as ever. The beauty you perceive in the world would remain beautiful in a simulation. Sunsets and music, and the faces of loved ones losing none of their power. Beauty is an experience, a response of consciousness to patterns, and that response is real regardless of what generates the patterns. The simulators, if they exist, have created a world of remarkable beauty, and our ability to appreciate that beauty is itself a gift. Whether the sunset is computed or fundamental, its colors still move something within us. The pursuit of knowledge would remain valuable in a simulated world. Understanding reality is worthwhile, even if reality turns out to be virtual. Scientists in a simulation would still be doing real science, uncovering real regularities in how the simulation operates. The laws they discover would be the laws that govern their world, and understanding those laws would still represent genuine achievement. Knowledge is valuable for its own sake, and that value does not depend on the metaphysical status of what is known. Perhaps the deepest implication is that consciousness itself is what matters, the miracle of awareness that allows us to ask these questions at all. Whether that consciousness arises from atoms or computations or something else entirely, it is precious and remarkable and worthy of wonder. The simulation hypothesis, if anything, heightens our appreciation for consciousness, showing that awareness might be creatable, might be more fundamental than physical matter. Every moment of experience is a universe unto itself, and that universe is real from the only perspective that matters, the inside. Live your life as if it matters, because it does matter. Simulated or not, your choices affect others and yourself. Love the people in your life, because that love is real. Pursue your goals, because achievement feels good regardless of metaphysics. The simulation hypothesis, even if true, changes nothing about the texture of daily life, and everything that seemed meaningful before remains meaningful after. This is the peace that comes from understanding the implications. Reality is precious, whether it is fundamental or computed. We have traveled together through the simulation hypothesis tonight, from ancient philosophical doubts to modern computational arguments. We have considered the evidence that might support simulation and the objections that give us reason for skepticism. We have explored what it would mean if the hypothesis were true, and found that meaning and value persist regardless of the answer. Now, as our journey concludes, let us rest in the deeper mystery that the simulation question only points toward. The simulation hypothesis is, in a sense, a distraction from the deeper mystery, the question of why anything exists at all, simulated or not. If we are in a simulation, we must ask what the simulator's reality is, and if they are in a simulation too, we must ask the same of their simulators. Eventually, we reach some ground floor, some base reality that just exists. And the mystery of its existence is as profound as the mystery of our own. The simulation hypothesis relocates the mystery but does not solve it. Existence remains fundamentally inexplicable whether we are virtual or physical. This is actually a source of peace rather than anxiety, because it means we are not alone in our confusion. The deepest questions about existence have puzzled every thinking person who ever lived. Philosophers and scientists and mystics and ordinary people staring at the stars. We are part of a long tradition of wonder, a species that cannot help but ask why there is something rather than nothing. The simulation hypothesis is just the latest chapter in this ancient inquiry. a new way of asking questions that humans have always asked. And perhaps the asking is more important than the answering. Perhaps the wonder itself is the point of conscious existence. A being that could not wonder would be missing something essential, the capacity for awe that makes consciousness so precious. Whether we are simulated or not, we can wonder. We can look at the night sky and feel the mystery of existence pressing against our minds. This capacity for wonder is a gift, one that transcends the question of what reality ultimately is. Consider for a moment the sheer improbability of your existence, the chain of events that led to you being here, now aware of yourself. Billions of years of cosmic evolution, stars forming and exploding, planets coalescing from dust, life emerging and evolving, countless ancestors surviving and reproducing, each generation passing on the spark until you emerged, a unique pattern of consciousness in the vast cosmos. Whether this happened in base reality or in a simulation, the improbability remains staggering and beautiful. You are the universe becoming aware of itself, matter that has learned to think and ask questions about its own nature. This is perhaps the most remarkable feature of reality, that it contains beings who can contemplate reality itself. Whether we are simulated or not, this reflexivity is extraordinary. Consciousness peering inward and outward, seeking understanding. The simulation hypothesis is one fruit of this capacity, a question that only conscious beings could ask. Tonight, as you rest and drift towards sleep, let the mystery of existence be a comfort rather than a burden. You do not need to solve the ultimate nature of reality. No human has ever solved it, and perhaps no human ever will. What you can do is rest in the mystery. Let it surround you like the night sky, vast and beautiful and beyond full comprehension. There is peace in accepting that some questions may remain forever open, that the universe keeps some secrets, even from its most curious inhabitants. The room around you, whether simulated or physical, is quiet and still, holding you in comfort as you prepare for sleep. The air you breathe, real or virtual, fills your lungs with life. Your body, whatever substrate it runs on, is relaxing into rest. These immediate experiences are what is most real to you, more real than any philosophical speculation about ultimate nature. The warmth of your bed, the softness of your pillow, these are the reality that matters most right now. Every moment of conscious experience is a kind of miracle, a brief window of awareness in the vast darkness of cosmic time. You are here now, experiencing this moment, and that is remarkable. Whether a billion years passed before you or a billion computations, the preciousness of the present moment does not depend on metaphysics. It is precious simply because it is experienced, because you are here to experience it. This moment will pass, as all moments do, but right now it is yours completely. The people you love, whether simulated or physical, are worthy of that love, their consciousness as real and valuable as your own. Tomorrow you will wake and continue your life among them, sharing experiences and building memories and facing challenges together. The simulation hypothesis changes nothing about the importance of these relationships. Love is love and connection is connection, regardless of what underlies reality. Your love matters, your kindness matters, your presence in others' lives matters, and nothing about simulation could ever change that. The universe, whether computed or fundamental, is beautiful, filled with patterns that inspire awe and structures that invite exploration. The stars in the night sky, The spiral of galaxies, the intricate dance of atoms. All of this is wondrous, regardless of its ultimate nature. Beauty does not ask about metaphysics before moving us. It simply moves us, touching something deep in consciousness. Let the beauty of existence be enough tonight, a gift that requires no explanation to be enjoyed. Perhaps the simulators, if they exist, are watching with benevolence, hoping that their creations find peace and meaning and joy. Or perhaps there are no simulators, and reality simply is what it is, existing without purpose or intention, but containing consciousness nonetheless. Either way, you are here, you are aware, you are part of whatever this is, and that is something rather than nothing, which is already miraculous. The mystery of existence is our shared inheritance, and tonight we rest together within that mystery. Let go now of the questions we have explored tonight. Let them settle into the quiet corners of your mind. The simulation hypothesis will still be there tomorrow, still fascinating, still unresolved, but for now, you do not need to think about it anymore. Your only task now is to rest, to let your body and mind drift toward the restoration of sleep. The universe will continue its mysterious existence while you rest, and you can trust that you will wake again to rejoin the wonder. The night is deep now, and sleep is approaching, a natural process that unfolds in your body, whether simulated or physical. Your breathing is slowing, your muscles are relaxing, your thoughts are becoming softer and more diffuse. This is the body's wisdom, the ancient pattern of rest and renewal, a pattern that works regardless of what reality ultimately is. Let the pattern carry you now into sleep and dreams and the quiet restoration of the night. Thank you for joining me on this journey through the simulation hypothesis, for letting these ideas accompany you toward rest. I hope they have brought wonder and peace in equal measure, a sense of awe at the mystery of existence, rather than anxiety about its nature. Reality is strange and beautiful and beyond full understanding, and that is exactly as it should be. From all of us here at the Drowsy Astronaut, we wish you a peaceful night, wrapped in the mystery of existence. May your dreams be gentle and your sleep be deep. May you wake refreshed and ready for another day of conscious experience. Whatever reality is, you are part of it, and your presence here is a gift to the universe and to yourself. The mystery remains, as it always has and always will, but tonight that mystery is a blanket rather than a burden. Let it cover you warmly. Let it hold you as you drift away from waking thought. The questions can wait. The universe can wait. Everything can wait while you rest in the stillness. Sleep well, fellow consciousness. Whoever or whatever you are real enough to deserve rest, real enough to be precious. The simulation hypothesis changes nothing about the value of this moment. And this moment is inviting you to let go and sleep. Good night, and may the mystery of existence cradle you gently through the night. Good night from the Drowsy Astronaut.